Today we will start lecture 5-3 on operational amplifiers. In particular, we will introduce three types of operational amplifiers, including ideal, inverting, and the summing amplifier. By the conclusion of this lecture, students should be able to write the formulas for inverting and non-inverting, as well as summing amplifiers, and clearly explain what each of the terminals on the amplifier do, and be able to use KCL in order to determine the output, the gain, current, and power for an operational amplifier. In addition, students should be able to explain the two basic assumptions we make in order to analyze ideal operational amplifiers. An operational amplifier is a voltage-controlled voltage source. This is the first of this type of circuit element we've seen because everything so far has been a two-terminal device, but an op-amp actually has 5 terminals. And because it's a voltage-controlled voltage source, it can be used for mathematical operations such as addition, subtraction, multiplication, and division, as well as differentiation and integration. Let's look at the op-amp. The circuit symbol that we use for the op-amp is on the bottom right. Notice that it has 5 terminals. It has a negative or inverting input. It has a positive or non-inverting input. It has the V positive and the V negative, which are the power rails, which represent the positive and negative voltage, and an output V naught. Unlike all of the other circuit elements we've examined in this course so far, an op-amp must be powered. So the V positive and the V negative are typically connected to positive and negative 12 volts or 15 volts in order to power the op-amp. It will not work if you don't attach the power. The bottom left figure shows the chip version of an op-amp, and it's an integrated circuit. So what you'll see in your kit when you do your lab is something that looks a lot like that chip on the left. Notice that there are 8 pins on it, but there are actually only 5 that we're interested in, including the inverting input, non-inverting input, V positive, V negative, and the output. The voltage characteristic of an op-amp has a linear and a nonlinear region, and we will take a look at this. Basically, it's decided by the power rails. So when the op-amp is operating in the linear region, the output is equal to the difference in its input voltage times the multiplying constant or the gain, and it's in between the power rails. You can never get more voltage out of an op-amp than what you power it. So in other words, if the power is positive and negative 15 volts, you're never going to get more than positive or less than negative 15 volts on the output of the op-amp. When you're outside of the range of positive or negative, the power rails, the op-amp is said to be in saturation or operating in its nonlinear region. This figure here shows what that would look like, where the slope of the line is actually the gain on the op-amp, and then positive and negative saturation is when the output has exceeded the power rails. There are 2 constraints or assumptions that we make for an ideal operational amplifier. The first one is the virtual short condition, which means that the voltage at the positive terminal equals the voltage at the negative terminal. In this class, we assume all op-amps are ideal. We will always use these assumptions to analyze the op-amp. The second one is that the op-amp has infinite input impedance, which means that I positive equals I negative equals 0 amps, or the current into the positive and the negative terminals is equal to 0. With these 2 ideal assumptions and KCL, it is possible for us to solve any op-amp problem. Okay, let's look at how we use these ideal assumptions to find the gain for an inverting amplifier. This first op-amp is called an inverting amplifier because the input voltage is tied to the negative terminal and the output actually has a negative gain. The gain is the ratio of the output over the input of the op-amp, and it inverts, which means that if you put in a positive number, you get out a negative number. If you put in a negative number, you get out a positive number. So I'm going to draw the op-amp here. Here's VI, the resistor that connects it to the negative terminal. There's the ground, and there's the feedback resistor that connects the output back to the input. So now we're going to use KCL in our ideal assumptions to derive the gain expression. First, we see that the positive terminal is tied to ground, which is 0 volts. Based upon the virtual short condition, if the positive terminal is 0 volts, the negative terminal is 0 volts. That's how we use our first assumption. So now if we were going to do KCL at the negative terminal, we would have 0 minus VI over RI. This is RI. Plus 0 minus VO over RF. The way we use the second assumption is that since we have infinite input impedance conditions, there's no current that flows into that negative terminal on the op amp. So in the KCL equation, there's no other currents, so I set this equal to 0. So now if I solve for VO, VO is equal to negative RF over RI times VI. So the output is equal to negative RF over RI times the input voltage, which means that if I were to derive the gain, which is equal to the output over the input, that would be negative RF over RI. So for example, if RF is 2 kilo ohms, RI is 1 kilo ohm, and VI is equal to 3 volts, then the output would be equal to negative 2 over 1 times 3, or negative 6 volts. The gain for this op amp would be negative 2. Note that an inverting amplifier can be an amplifier or an attenuator. Amplify means to make bigger, which means if the gain is greater than 1, you amplify the input to get the output. If the gain is less than 1, then you attenuate or make the input smaller. So for example, let's say I reversed RF and RI. So now I would have RF is equal to 1 kilo ohm, RI is equal to 2 kilo ohms, and VI is still equal to 3 volts. The output would now be equal to negative 1/2 times 3, or negative 1.5 volts. So this has inverted and attenuated the input. Now let's derive the same relationship for the non-inverting amplifier. Okay, so this is a non-inverting amplifier. What makes it non-inverting? Well, the input voltage is tied to the positive terminal. We'll always have a feedback resistor from the output to the negative terminal. The negative feedback is what causes our ideal assumptions. And we also have an input resistor that's tied to the negative terminal. So let's sketch the op amp, and then we'll use KCL to solve. So here's the negative and the positive terminal. Here's the input voltage at the positive terminal. Here's R1 tied to ground and the negative terminal. And here is the feedback resistor and V out. So first, since the positive terminal is tied to the input voltage VI, based upon our virtual short condition, the negative terminal must also be VI. So now we're going to do KCL at the negative terminal. We're going to have VI minus 0 over RI plus VI minus VO over RF. Recall that there's no current flowing into the op amp. That's 0 amps, and that's our infinite input impedance condition. So this equals 0. When I solve for VO, VO is equal to 1 plus RF over RI times VI. So the gain for a non-inverting amplifier would be equal to 1 plus RF over RI. This is very important to note that there's 1 plus RF over RI, the gain for a non-inverting amplifier. A common mistake students make is to make the gain for the non-inverting RF over RI because the inverting is negative RF over RI. Because this is 1 plus RF over RI, a non-inverting amplifier is purely an amplifier. There's no way to get a gain equal to 1 or less than 1 out of a non-inverting amplifier, so it always amplifies the input. Let's look at an example. If RF is equal to 2 kilo ohms, RI is equal to 1 kilo ohm, and VI is equal to 3 volts, what's the output? The output is 1 plus 2 over 1 times 3, which is 3 times 3, or 9 volts. And that makes the gain equal 3. Well, what if I reverse RF and RI and make RF equal to 1 kilo ohm, RI equal to 2 kilo ohms, and VI still equal to 3 volts? Well, VO is equal to 1 plus 1 over 2 times 3. So that would be 3/2 times 3, or 4.5 volts. So the gain is 1.5. The last type of op-amp we'll look at today is a summing amplifier, or an inverting summing amplifier. Why is it called inverting summing? Because what you'll notice here is that all of the voltage inputs are tied to the negative terminal and all of the gains are negative. We won't actually do KCL in order to find the output for this one, but we will do superposition. What this means is that if we turn each of the input voltages on one at a time, what's the output? If only V1 is on, what you'll see is that these other two are grounded, which makes their input 0. And now this looks just like an inverting amplifier that we had before. So VO prime would be equal to negative RF over R1 V1. Similarly, if we turn on V2, VO double prime would be equal to negative RF over R2 V2. And if we only turn on V3, VO triple prime would be equal to negative RF over R3 V3. So the output for the summing amplifier would be negative the quantity RF over R1 V1 plus RF over R2 V2 plus RF over R3 V3. So this is actually a weighted sum because the gains for RF over R1, RF over R2, and RF over R3 don't necessarily have to be 1, and they don't have to be the same. And it inverts because of the negative sign. Okay, let's try an example. For the following circuit, assume the op-amp saturates exactly at the rail voltages. What range of input voltages will avoid op-amp saturation? So one thing we always do in solving these problems is assume that the op-amp will saturate at positive and negative 15 volts, or whatever the rail voltages are. This is actually not true, and you will see this in lab. The op-amp actually saturates about 1 or 1.5 volts before the rail voltages. So in lab, if you have 15 volt power supply, you will see that the op-amp actually saturates at 13.5 volts. But for the purpose of our analytical calculations, we always use the numeric value of the rail voltages. So first, what type of op-amp is this? The voltage is tied to the negative terminal. The positive is tied to ground. So from what we just discussed, we know this is an inverting amplifier. The gain is equal to output over input, which is negative RF over RI. Remember, RF is the resistor that ties the output back to the negative terminal. So that's negative 20 over 10 or negative 2. So the output is equal to negative 2 times VI. Since we're assuming the op-amp saturates between negative and positive 15 volts, we need to keep the output between negative 15 and positive 15 volts. So that means that negative 2 VI must be between negative 15 and positive 15 volts. So the range of input voltages that would avoid op-amp saturation would be VI between negative 7.5 and positive 7.5 volts. If I drew a sketch of the input and output relationship for this op-amp, what you would see is I have VO on the vertical axis, VI on the horizontal axis. And because it's an inverting amplifier, I'm going to have a negative slope that has negative 7.5, and it's going to saturate at negative 15 volts and positive 15 volts. Okay, here's our next example. For the following circuit, assume the op-amp saturates exactly at the rail voltages. What range of rail voltages will avoid op-amp saturation if VB is between negative 4 and 5 volts? So first, let's identify what type of op-amp this is. The voltage is tied to the positive terminal, but we once again have a feedback resistor and a resistor tied to the negative terminal. So this is a non-inverting amplifier. Remember, the gain is output over input, which is 1 plus RF over RI for this circuit, or 1 plus 50 over 25. So the gain is equal to 3. So V out is equal to 3 VB. So we need 3 VB, which is the output, to be between the positive rail and the negative rail. So if VB is equal to -4, we need -12 to be between the negative terminal and the positive terminal. And if VB is equal to +5, we need 15 to be between the negative terminal and the positive terminal. So what that would mean is if we let the negative terminal equal -12 volts and the positive terminal equal 15 volts, then the op amp should not saturate. So this one would be -12 volts. This one would be 15 volts. Okay, so now let's draw the input and output graph for this op amp. I'm going to put the input voltage on the horizontal axis, the output voltage on the vertical axis. Now it's a non-inverting amplifier, so it should have a positive slope, and that slope should be equal to 3. When the input reaches 5 volts, the op amp should positively saturate at 15. And when the input reaches -3, it should saturate at -12. Let's try our next example. The following circuit is not one of the standard configurations we have discussed so far. How can you find V0? What is V0? Well, there's 2 ways to actually do this problem. One is to use the ideal assumptions in KCL to solve, and I can do that. And the other one is to use superposition. Let's do the ideal assumptions first. So the ideal assumptions and KCL. So V positive is equal to 2 volts. So V negative would be equal to 2 volts. So then if I do KCL at V negative, we have 2 minus 6 over 20K plus 2 minus VO over 40K, and that equals 0. So when we solve for VO, VO is equal to -6 volts. Our other alternative is to do superposition. To do superposition, you turn each of the inputs on one at a time. So let's say I turn the 6 volts on first. I'll have 6 volts. The positive terminal is grounded. My feedback resistor is still 40 kilo ohms. My input resistor is still 20 kilo ohms. And this is VO prime. What type of op amp is that? The voltage is tied to the negative terminal. The positive is tied to ground. That's an inverting amplifier. So V0 prime is equal to -40 over 20 times 6, or -12 volts. So now we need to turn the 2 volt on and the 6 volt off. So I'll ground the 6 volts. Here's my input resistor, which is 20 kilo ohms. There's my negative terminal, my positive terminal. The feedback resistor, which is 40 kilo ohms. The output is VO double prime. And at the positive terminal, I have 2 volts. What type of op amp is that? The voltage source is tied to the positive terminal. This is a non-inverting amplifier. So VO double prime is 1 plus 40 over 20 times 2, or 3 times 2, which equals 6 volts. So the output would be equal to VO prime plus VO double prime, which is -6 volts, the same as what we got before. So the thesis statement of this discussion is that even if you don't know what type of op amp you have, ideal assumptions, KCL, superposition always work. Now let's look at in-class activity 4. We have an op amp here. What type of op amp do you think this is? Well, let's think about here that the positive terminal is on top this time instead of on the bottom, but that doesn't change the op amp configuration. There is an input voltage. There are 2 resistors, but there's still an input voltage and it's tied to the positive terminal. So this is actually a non-inverting amplifier. It's upside down from what we've seen before, but it is a non-inverting amplifier. The feedback resistor, RF, is 5 kilo ohms. And the input resistor, Ri, is 2 kilo ohms. So that non-inverting amplifier has a gain of 1 plus 5 over 2. Now let's talk about what's going on at the positive terminal. If I call this VP, the gain on VP is 1 plus 5 over 2, or 3.5 VP. So the difference between this and what we've seen before is this was a voltage source. Now it's a voltage, but the voltage source, 3 volts, is not the voltage right there. How can I find VP? Well, if I look here, because of my infinite input impedance condition, there's no current flowing into the positive terminal of the op amp, which means the current that comes from the 3-volt source goes down through the 8K resistor. So this looks like the 4K and 8K resistors are in series. So to find VP, I can actually do the voltage divider. VP would be equal to 8 over 4 plus 8 times 3, which is 2 volts. So now, if I want to find the output would be equal to 3.5 times 2, which equals 7 volts. Okay, here's our last example for today's lecture. What type of op amp do you think this is? It has multiple inputs. They're all tied to the negative terminal. We've actually only seen one of these types. It is called a summing amplifier or inverting summing. And remember, the output is equal to the sum of all of the inputs with the gains based upon their resistors, and then you invert it. So for this one, that's going to be negative 8K over 20K, or 8 over 20. So V naught is equal to negative 8 over 20 VA plus 8 over 10 VB plus 8 over 6 VC. Now let's redraw this and reduce those fractions. So we're going to have negative 2/5 VA plus 4/5 VB plus 4/3 VC. So now we're giving that VA is 1.2 volts, VB is 1.5 volts, and VC is 2 volts. So VO would be equal to negative the quantity 2/5 times 1.2 plus 4/5 times 1.5 plus 4/3 times 2. So VO is equal to negative 4.35 volts. Now, something to think about. A common mistake students make is to assume that because the infinite input impedance means there's no current flowing into the negative and positive terminal on an op amp, that there's no current coming out of an op amp. This is absolutely not true. There's current coming out of the op amp because there's current coming from the rails on the power supply. So the current coming from those rails goes out of the op amp. Remember, the ideal assumption is no current comes in. That means the current is actually negligible. There may be a very small current, but it's negligible. But there is current flowing through the power rails, and some of that goes out of the op amp. So the way that you find I naught is you use KCL. KCL for that node would be that IO, the current into the output node, is equal to the current through the 8K resistor plus the current through the 4K resistor. So in this case, IO would be equal to negative 4.35 over 8K minus 4.35 over 4K. Remember, this is ground, so it's 0 volts, and this is 0 volts based upon our ideal assumption, which is why it's just negative 4.35 over 8K. So finally, I/O is equal to negative 1.63 milliamps. This concludes our introductory lecture on operational amplifiers.